Hello everybody. I am Mohamed Gabry, uh, 10 years experience in fracturing and graduate research assistant at University of Houston. Uh, Today we'll talk about uh, the most commonly used fracture simulator in the industry, which called GOHFER. I believe you have some basics of hydraulic fracturing and some knowledge in hydraulic fracturing operation. So let's take a quick session and get some hands-on how to use GOHFER. It's one of the most powerful most powerful fracture simulators that you can start with to create your own design. Simply, GOHFER is a abbreviation of Grid-Oriented Hydraulic Fracture Extension Replicator. It's introduced in the industry by Dr. Robert Barry. Dr. Barry, his PhD was in fracture simulation and GOHFER. So it's introduced the simulation equations introduced at 1987. So since this year, it continue to update and add modules in GOHFER. So it has some practical experience, and it provide a flexible tool to design and match your hydraulic fracturing job. GOHFER is owned by Dr. Robert Barry, and Halliburton bought that software. So it's now bought all the company. So this GOHFER is owned by Halliburton since 2009, 2020. GOHFER has a lot of modules for well construction, for petrophysical and geomechanical interpretation, the fit analysis, completion optimization, production forecast, completion design, and the crying curve or transient analysis. But the main concept for GOHFER is for modeling for hydraulic fracturing. As we will open together the software, and we will discuss together how it performs. Let's revise together the main concepts of hydraulic fracture modeling. Since starting of the modeling for hydraulic fracturing, the modeling started with 2D models, KGD model and BKN, Birken, Kern, and Nordgren, and KGD model, Kristinovich, Gristima, de Klerk. So one of them assume the fracture propagates in length, and the net pressure increase with propagation in length. The other one assume the propagation in height. So it's possible in the start of hydraulic fracturing job, and it applied when the net pressure drop with fracture growth. And this is the start of the modeling. Then these two models, KGD and BKN, commingled together and combined together to create the pseudo 3D model. Pseudo 3D model assume the fracture propagate in height and in length in same time. So once the pressure drop, the net pressure drop, it assume fracture propagation in height. Once the pressure drop, the net pressure increase, it assume propagation in length. So, but both of them has a lot of simplification, simply because they assume the base zone has only one geomechanical parameters. So there is some simplification, some averaging for reservoir properties. although there is some there is in the industry there is some types of pseudo 3D model. One of them get some details in modeling, which called the pseudo 3D model that we can see in Frackade by Schlumberger, and the lumped pseudo 3D model. It simulates the fracture as a balloon or lumped propagation, as we see in FragBrew. So FragBrew is lumped based pseudo 3D model. Schlumberger Frackade cell based pseudo 3D model. The main, as we know, the main problem of pseudo 3D model is the averaging over the base zone and over the area covered by hydraulic fracturing. And also there is 1D fracture propagation, 1D fluid flow. So we assume the fracture to propagate from wellbore toward the fracturing. So the fluid flow in this direction is not simulated in this old models, although there is some modeling, some companies still use FragBrew and Frackade in their design. So the next step in fracture modeling is planar 3D model. Planar 3D model, simply we divide the reservoir into 2D cells. So we have more grading in the reservoir properties, and we assume the fracture propagate in this two direction in the fracture propagation plane. So it's called the planar 3D model. Fluid flow in two directions. So the pressure loss for fluid flow in this two direction. As all the simulation during the fracture propagation, the height of hydraulic fracturing is calculated using net pressure concept with stress difference. So Simonsen et al. Approach. So planar 3D model is more add more advanced options. So we can divide our reservoir into grids, then apply hydraulic fracturing. So no more averaging, so no more approximation. Now we have more detailed and more, we can simulate with more complication of our reservoir. So the main parameter for fracture simulation now is not averaging, but it's simulated grid by grid. So our mission today is to create these grids with GOHFER and apply hydraulic fracturing, and GOHFER will simulate the fluid flow from the wellbore into the reservoir, and once we distribute the properties in the grid, we can create a fracture which propagate in the reservoir. And simply that is the main approach, the main timeline for hydraulic fracture modeling over the history. Started with 2D fracture model, the 3D model, Frackade and FragBrew, cell-based and lumped-based. Then planar 3D model, GOHFER, and there is more advanced fracture simulator than GOHFER, but it's not flexible like GOHFER. It's not practically used like GOHFER. In special projects where you have time to design your job and discuss a special reservoir fracturing and special and take your time, not day by day frac. So if your operation is very, very slow, you can go to the the full 3D model, where the reservoir is divided into 3D grids and distribute properties, and all details included in fracturing. But as you know, it takes a lot of computational time, a lot of computational cost in the processors that's needed for such models. So most of company prefer this handy tool which called GOHFER. Also, GOHFER has some benefits in log analysis. So let's discuss concepts. For any fracture simulator, simply we create the reservoir and create our well, then distribute the properties needed of reservoir that's needed for hydraulic fracturing. These properties commonly done by another software, log interpretation software like interactive petrophysics or TechLog or any special module for geomechanical parameter. So they create the properties of reservoir from well logging data or from core data to get Young's modulus. For fracturing, you need to define some parameters to simulate your frac. So you need to define your Young's modulus, your Poisson ratio, your for the reservoir, the toughness, and minimum horizontal stress. So, and several parameters to define your reservoir. Then apply the pumping schedule, which is mainly pumping rate and the fluid, using the fluid, and with the pumping rate and your probant schedule to get the pumping pressure that you need to design and estimate from the design. So simply, GOHFER has a good approach to work with any logging data that you have in your well. So any logging data, if you have gamma ray log, you can establish your geomechanical parameters. If you have any triple combo log, the most commonly used logs that you record in your log in your well, so it can work with a lot of logs that you log in your reservoir. So simply it's very flexible. It can work with any type of data, and this is the main advantage of GOHFER. The main we need to also, before start with GOHFER, we need to discuss the main stress concept of GOHFER because it creates the minimum horizontal stress creates the geomechanical parameter and the most important parameter that we need for frac design, the minimum horizontal stress. So it created from the well logging data. So this equation is done automatically by GOHFER. So based on the Young's modulus and the Poisson ratio and the vertical horizontal stress and vertical principal stress and the reservoir pressure, simply it calculates the minimum horizontal stress using this equation. So you need to make sure that the calculated Young's modulus and Poisson ratio and pore pressure is correct, and based on the accuracy of your data, it will calculate your closure pressure or minimum horizontal stress. GOHFER simply assume the vertical stress and vertical stress with gradient, constant gradient. We will adjust this gradient to be between 1 and 1.1, and assume reservoir pressure with the simplest pore pressure model with hydrostatic gradient 0.433. We can adjust these two gradients, then calculate the minimum horizontal stress using this base concepts, the vertical stress and the horizontal and reservoir pressure and pore pressure gradient 0.433. Then calculate based on Young's modulus and Poisson ratio using this equation. And as any software, the general concept of frac design, we define the well, we define the reservoir, then define the frac fluid and define the proppant, assume pumping schedule, and run the model to estimate the pumping pressure, to estimate the equipment needed to do this job, and get fracture geometry to enhance our reservoir as a conventional reservoir, or start the production as an unconventional reservoir, because in unconventional reservoir the permeability is very, very tight, so we need hydraulic fracturing to start the production from this reservoir. So let's this is simply the main concepts of fracture simulator and fracture modeling as a quick introduction. And let's open together the GOHFER. For any frac design, you need some data that you need to ask your reservoir engineer to provide. So you need to know what is the perforation. You need to know which type of from the completion data, which type of casing this is run in the well, what type of tubing that will be used in this hydraulic fracturing job. Basic reservoir parameters like porosity, the saturation, the BBT data, reservoir pressure, and the permeability. You need to know the permeability from different sources like RFT or DFET or well test analysis or any data. So you need any source of data. So you need to know the reservoir permeability and reservoir pressure and BBT, some data about your BBT for your reservoir and your reservoir temperature. So mainly you need some from your reservoir engineer. You need to understand how your reservoir and what is the properties of your reservoir fluid to start with your frac modeling or frac design. Simply, when you let's open together GOHFER. When you start GOHFER, you simply there is it's provided with a time limited license. So based on your license. So you can simply start GOHFER, and the first window you can simply it asks you to if you have any project before any projects that you created before or not. So you need, if you have any project to review, you can select the GOHFER project that you already created. If you didn't create any GOHFER model before, so you need to select the new GOHFER, new GOHFER project, and let's create our project, and select the place where you want to save your model, your project. Once you select the place of your GOHFER project, there is some introduction. What is the type of the oil field data, that oil field units that you need to use in your project, metrics or oil field units. Also, if you have a multiple stages, multiple treatment wells, like multiple fracturing, horizontal fracturing, you can select the multiple treatment wells. But if your case is a single vertical treatment well with no transverse fracturing, so you can select single fracturing. The main difference between these two types is in GOHFER, it has a log analysis module, and so you need to provide the data for pilot well, which you will use for geomechanical interpretation. Then create another treatment well, which is horizontal well, to start to implement your hydraulic fracturing job. So it's more advanced and more complicated interface, but the simulation itself is the same. Between the simulation for transverse fracture, multiple fracturing, and single vertical well. So, but the interface is more complicated because you run the well logging tool in a pilot well, and in another you conduct multiple treatments with otherwise either it's longitudinal or transverse fracturing in a horizontal well. So its interface will be more complicated. So for today's session, we will take case for the vertical well, then select OK. So now we have the basic interface for GOHFER. So simply we have here is the workflow for GOHFER. So we have well construction. It assumes as a start there is a reference well, where you start logging your data and building your geomechanical parameters, and there is a treatment well. And simply if it's the same well, so simply select reference well and use it as treatment well. So your well is the same as your treatment well is the same as your logging data well. So our case, our our case, we will use same well for the logging and for geomechanical model and for treatment. You define the well on GOHFER simply by two main windows. The first window from the survey. So once you get the survey from drilling guys, the measured depths, inclination, and azimuth, you can copy and paste here in this section, or if you have measured depths and TVD, you can simply paste this section. In our well, well is simply a vertical well, and we have a TD from our data at 12,810. So simply we have 12,810. So our well is created vertically, and if it's horizontal, you will show your well and get familiar with its survey and start to rotate it, and like any 3D visualization. So you define your well your survey for your well, but before working with the survey, we need to define, as we discussed, the two main parameters that we need to check. The first one is you can provide the data for the location of the well, the latitude, and the data for the well location for the wellhead. But the main parameter that we need to define is the used seawater, the used gradient that we use in pore pressure prediction. So if you are working with offshore data, you need to define also the seawater gradient to be used as for the reservoir pressure and for overburden gradient. And the overburden gradient, we need to confirm what is the data that we use for your design. So simply, if any number between 1.1 and 1 between 1 and 1.1 is correct, so let's use the midpoint between them. And if you have any model from simulation team in your company, you can import the model. You can import the model that's created using your GNG team to be imported in GOHFER, but with our current data, we don't have this geologic model. After you define the main administrative parameters and the information from your location, simply you can go to the reference well, and as we agreed together, we use it as a treatment well. If you didn't check this box, so you will define your geomechanical parameters in reference well, and conduct your hydraulic fracturing in a treatment well. So you need to define again in two separate windows your tubing data, your casing data, and so on in two different windows. So, but in our case, we use the same well for logging, for geomechanical parameters, and for your treatment. As we discussed, we can copy and paste from the survey the MD inclination and azimuth, and it will create the well survey. Our case is vertical, so our inclination is 0 and azimuth 360. So no great differences between the MD and the azimuth. So the MD and the TVD. Then we need to define our log to create geomechanical parameters. Geomechanical parameters that we need for hydraulic fracturing are mainly the Young's modulus, and specifically we need the static Young's modulus and Poisson ratio and minimum horizontal stress and toughness data, or the tip propagation data. So simply it can work with any type of data. So simply if you click on less, it will open a window for log analysis module. You can simply from the less file from your the data from the GNG or reservoir engineering. You can import several less file. If you have a lot, if you, for example, want to take the gamma ray curve from a less file and resistivity log from different less file, and the Young's modulus and Poisson ratio from different less file, simply you can import multiple less files and import whatever you need from each file. So I have the petrophysical analysis, the petrophysical data that's interpreted by the petrophysicist. He took the triple combo data, which is gamma ray resistivity and neutron density, gamma ray resistivity, neutron density, to create the volume of sand, volume of limestone, volume of dolomite, volume of shale, and imported and put it as a petrophysical interpretation. And also in this well, especially we recorded for the data, for well logging data, for fracturing purpose, we logged the dipole sonic log. So we will use the dipole sonic data, which is shear and compressional time. So we will use the DTS and DTC for our Young's modulus, for our mechanical interpretation. So simply we have two different less files, so I can import them. For any logging data, we calibrate the tool on to detect the main target for our well. So if you target your reservoir, if you target sandstone by the well logging tool, you calibrate the model to detect sand shale. So you can calibrate it use on carbonate, and if you use the logging tool to detect carbonate, you calibrate the model to be calibrate the model on sand shale to calibrate to detect the carbonate, and on shale carbonate to detect sand. So based on you can ask your GNG expert to what is the main goal for our well and our logging job, and what is the calibration for your tool. And simply because we detected here as a the main target for this logging is sand, so we calibrate the model on carbonate shale. And simply this logging data is very long logging data. So we need to assure that we define the geomechanical model to cover our base zone and to simulate the fracturing. So our base zone starts with 12,626 till the bottom of bottom berth is 12,720. So simply we can cut a part of this long less file just around this base zone. Simply you can select 1,000 above and 1,000 below, and just more than enough. So we need to select a 2,000 feet to cover our base zone. So let's select from 12,000 till 14,000. Okay. So that is what is the default values for this section. Simply it take from the bottom of last file till and 2,000 length, then put and import this section. This is the default values, but you need to, based on your base zone, you need to adjust the top of last file and bottom of last file that you need to use. So then finish. It will import all the data in GOHFER in log analysis module. From log analysis module, simply you can find that the module is divided into the some assigned curves. It has some boxes like boxes to put your curves. It has some auto capturing techniques and capability to capture some curves from the log that you imported, from the last file that you imported, but it sometimes it needs some help. So to review the data that we imported in GOHFER, we have the CPI, we have the caliber data, we have the logging data, we have the bay flag for the bay zone identification. So we have also dolomite, limestone, the volume of minerals. So, for example, it defines the V dolomite as it's defined as the standard name, but it didn't define the V sand. So it didn't consider that you imported V sand. It will calculate in the inside core in the core of GOHFER. It calculates the V sand, but the better petrophysical parameter is comes from your petrophysicist, which has experience with your data and the area of interest. So you need to define as much as you can and as much as possible. So you need to define the log that you imported into and make sure it's imported by GOHFER. Simply, you can move the vsend to vsend location. Let's for limestone vlime, for anhydrite vsalt, and vshale. simply if it by mistake, you can remove input, right click and remove input curve, and let's put it again, move it to V shape. If you have Young's modulus and you will use static Young's mod and your Young's modulus, simply you can import it from here. Now I don't have the 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 Young's modulus data. If you calculate stress from any different source, simply you can import it as a LAS file or text file, then import it as a curve between the depth and the value. So if for example, if you have RFT data, simply the reservoir pressure with depth, you can put it in Excel in a text file, then import it as a curve here, and so on. So any curve that you need to add and you want to add, so simply you can add it as a curve, as a input curve in LAS assignment. Generally, this if your icon, this icon is green, so you are okay. So you have, and the data is assigned successfully. If for any reason there is a red icon, so it's not, you need to assign it again. Maybe there is depth mismatch or values mismatch or any other reason. And if it's yellow, so yellow means it's need to be reviewed. So once you open the icon, the logging curve, you simply and if it's okay, so it will turn into green curve. So simply it for our model, we also you can import any other data or any logging curve. Simply here it's automatically imported the TTC, the compressional curve, the compressional time curve. So it imported automatically. Then you need to check it and review your data for quality control, for QAQC reasons. Then let's start to create our geomechanical parameter. Let's remember together how to create the geomechanical parameter. Simply, the Young's modulus and Poisson ratio is calculated using the equations from the dipole sonic log, from DTS and DTC. If you don't have this data, so you can use different logging techniques to get this data, but it will be less accurate simply because it's a correlation, not a calculation. So from dipole sonic log data, you can create the dynamic Young's modulus and Poisson ratio using the equations. Then convert it to a static using a core data or local correlation to get the static Young's modulus and Poisson ratio. From static Young's modulus and Poisson ratio, we use the fraction simulator to calculate, or that's what can be used by fraction simulator. So any fraction simulator use static horizontal Young's modulus and Poisson ratio. And in GOHFER, we use this data not only for fraction simulator, but also to create the minimum horizontal stress curve to estimate the minimum horizontal stress, whereas we create our fracture design. Then, after we assign our curves, we need to go through each curve to and confirm it's calculated in the right way. Simply, if you here it imported the gamma ray. So, for example, if I have two gamma ray curves, which one? What is this curves? Simply, if you selected any curve, any category for curves, so then you enlarged this curve, this properties window. Simply, it will tell you what from the source of this curve. So, for example, this curve is from this file, and the other one from the other file. So I have the source for, I know the source of these curves. If you select the category of curves like gamma ray total, so it will give you some general information. So you can simply, for example, here we have a minimum and maximum scale for gamma ray. If I want to change the scale of this curve, simply I can assign here, for example, 300, convert to 300. If I did 100, I can simply change the scale as I can, change the color, change the, if I want, for example, to shift it for with a certain value, or the shifting or scaling or powering your, make it to the power of any number, or apply logging data. So it's very flexible tool to assign to work with your logging data. Actually, I even if I want to use FragBrew or FragKit, so I prefer to create the geomechanical parameter using GOHFER. It's very flexible way, flexible tool to create your geomechanical parameter. As you know, for when you work with gamma ray, so you need to assign sand line and shade line, the minimum and the maximum for shade. So you need to confirm your log is bounded in between sand line and what is 100% sand, and shale was 100% shale. Then once you define the gamma ray, then go to the next curve. Simply, we need to go through each curve category to confirm it's well captured and it's well calculated. So from the RHOB, simply it captured the density log from RHOB, and this is the name, its name in last on this last file, and simply we can here. So if, for example, if you have any other density curve, so simply import it here from add last file, then it will make it as a expandable file. Then simply take this file and import it in under the RHOB or any other logging box that you want to work with. For example, if I, for RHOB, it has only one curve RHOB, so this curve will be taken as a bulk density. Then the gamma ray. So if you selected gamma ray, so you will find a lot of sub gamma rays that inside this gamma ray box. Simply, you can decide which one to take simply by if you selected the property of this box and selected the calculation. So there is different types of importing this curve or dealing with this box. Average, it will take average for all curves. If you select smart average, it will take weighted average for each curve. If you select maximum, it will, based on this point, it will take the maximum value from each, the maximum value in comparison between in comparison between all of these curves, and so on. We imported gamma ray in GOHFER, but it calculates also another GOHFER from from other logging data. So if you want to compare between them, so no problem. If you want to ignore the calculated gamma ray from GOHFER, simply you can right click and remove input curve, and so on. Then the neutron density, we need to confirm that we capture the GOHFER captured the right log from the average porosity. You can select and confirm it's calculated right. Average porosity is a calculated value inside GOHFER with different modules, right mean square or arithmetic mean, or and this is the approach for average porosity in GOHFER. The effective porosity, simply as GOHFER estimate the effective porosity, but it also can be captured or imported from the well logging data. The byte coefficient, it calculates one of the main curves that used intensively from GOHFER by GOHFER is the effective porosity. So make sure that your betophysicist worked well with this effective porosity, and because most of calculated parameter are based on the effective porosity curve. The resistivity, you need to assign the right curve. For example, here to select between any, if you have the box with multiple curves, simply drag the curve till the top. Once it reaches the top and the box is selected to be copy means it will take the value from the first curve, and so once I select copy and drag the curve to the upper one, to the top of the rest at the box, so you can use it as a from this curve. So as you know, the geomechanical parameters calculated from the dipole sonic log. So the dipole sonic log calculate the Young's-Mills Boson ratio, and from Young's-Mills Boson ratio with overburden and reservoir pressure, you can calculate the geomechanical parameters. But what if we don't have any dipole sonic log? We are lucky now to work with the geomechanical to work with dipole sonic log. But what if there is, for any reason, you didn't log this high cost log? Simply, GOHFER introduced a solution to build a linear regression module between different log data and its dipole data. So it creates synthetic time synthetic DTC and the synthetic DTS to and compare it from the different logging data to create the geomechanical parameters. So we, from the logging data using correlation inside the implemented and included inside the GOHFER, we can create synthetic DTC and synthetic DTS. And now we don't need to do that simply because we have DTC and DTS from the sonic, from the sonic log, the dipole sonic log, the perf, the second logging data. But you can also due to some QAQC errors in your DTC and DTS that you recorded, you need to compare between different sources of data and calibrate the linear regression model that you created using GOHFER. So if you right click and on the box, the upper group of log of well log data, and we create log assistant. Select well log assistant. For example, it will create a linear regression between resistivity and the DTC from resistivity, and that's done on different properties. So from gamma ray, from phi A. So you need using GOHFER because it creates multiple correlations between different parameters and the synthetic DTC or DTS. Then using these correlation parameters, it should give you the same curve at the end. So you need to calibrate all the curves on one curve, which is the DTC actual, the recorded one. And if you don't have a recorded DTC or DTS, simply you can use what GOHFER calculated using different parameters. The main concept is it's a linear relationship between the property like resistivity or phi A or any property with the synthetic compressional time that's created using GOHFER. Simply, it creates different curves, so you can match these linear parameters. For example, AutoFit. So it can create different relationship between the properties and any property and the DTC for this property. Then simply you need to make them give the same answer. So you need to change the offset and the scale for this equation to give same number which match the recorded one. So or match each other, because it's at the end, it's the same formation that, so the Young's modulus created from gamma ray should be the same Young's modulus and Boson ratio, and the same Young's modulus that created using, for example, the neutron bursts and so on. So we change it simply, it changes the offset and scale to match the linear relationship between the property and the DTC and its DTC and gamma ray. So here's the matched curve. So all curves are matched. So we need to match the curves at non-Bay zone, because Bay create errors in dipole sonic log and in logging data. So simply you can match the parameter, the correlation parameter, the scale and the offset. Simply by changing the scale and the offset, you can match the parameters, the synthetic DTC and the synthetic DTS, to match each other. So all of them agree on same DTC and DTS value. And with same concept, we do like the same concept for DTS. It's done using DTC and all the correlation parameter already optimized on DTC. So same optimization parameter and same correlation parameters used with DTS, and but we need to confirm that it's captured successfully, and the right curve is imported in your log analysis module. The Poisson ratio also with same concept is applied. So we need to change the parameters to match most of the data. So if you select auto match, and for sure you want to match the actual data that you recorded, so you can match the correlation parameters from for the Poisson ratio and for the Poisson ratio, Young's modulus and DTC DTS. Simply you can match all the parameters to be match each other. So you confirm by the matching that you have the matching of the result using the correlation parameters. You make it more confirmed about the right geomechanical parameters. So we created multiple curves. So there is some mismatch here for the actual one, but I think it's Bayesian. So here's good match. So we can leave it. If any curve doesn't match with you for any reason, you can simply remove it and work with the other curves. We need to make sure that you understand carefully the concept of correlation, because it uses simply the correlation parameters AX and B, the A and B, to match the property with DTC or Young's modulus or Poisson ratio from this property. Then once you make the correlation parameters, all the curves match each other, so and match the recorded one, so it's the most accurate. So it's the most accurate that geomechanical parameter that you can use. The same concept with Young's modulus, using the correlation and this correlation parameters A, X, and B, you can match all the curves together. So simply you can outfit, auto fit. So our curves here, if you know these curves, so there is some area in some accepted match, some away match, there is some curves away from other curves. So that if there is odd curve, you can simply remove it, because we need to confirm that all the properties, all calculated properties for the same rock, so it should together match with each other. And for Young's modulus, static Young's modulus, because that's what there is a correlation that from the dynamic Young's modulus to create or calculate the static Young's modulus, the most accurate data for the relationship between static Young's modulus and the dynamic Young's modulus is to take core and apply the geomechanical tests to get uh, uh, the static Young's modulus and boson ratio. Brittleness factor, it's used simply to select the fluid or to manage your fracturing operation. So no need to change it, because we don't actually use it in our frag design. Net bay, simply if there is a net bay identification module in GOHFER, but the best net bay identification module is from your petrophysicist. So simply you can add bay flag here. So, and this is the bay zone that's defined by our reservoir only. This is only the bay zones that's defined by the reservoir engineer and the petrophysicist. Poor offset is the amount of increase or decrease in reservoir pressure compared to the hydrostatic gradient. As we discussed earlier, GOHFER has a static, a hydrostatic gradient, which is 4.44 or 0.433. Then any overpressure due to compaction or depletion added to this these two curves. So the amount of depletion or compaction, the increase in pressure due to compaction, is defined using pressure offset. So it's for my example, it's standard to be 0, but if you need to add general offset value for the reservoir pressure or core pressure, so you can put it here for X shift. But if you, for example, you need if you want to for a specific depth, so you can simply bring the pen and define a curve or a part of curve with this value. Pore pressure gradient is calculated or assumed to be constant, so it's estimated to be constant. Then add pressure offset, which represent the depletion or overpressure of your reservoir. Then you confirm that you captured the right water saturation, the propant holdup. It's calculated value from the phi e, which represent how your fracture will handle propant transport. Transmissibility factor. It's all of them has a minor effect on fracture simulator. Strain for this model is considered to be 0 because we don't have a tectonic active places, or in our case, or any tectonic events that happened earlier to create this strain effect, the current stress effect. If you want to change the stress value with a straight value, with a specific value, you can change the stress offset. Any curve that you want to change, simply for a certain depth, you can bring the pen to change the stresses or change this curve generally, but to change the value for this curve at this depth. Or if you want to add generally, simply open the category, the group of curves, then add a value here in shift, scale, or power or log. So it's very flexible to create whatever you want. And this is the main horizontal stress that's calculated. Our reservoir data is confirm the reservoir pressure to be 5,500 psi. So let's confirm it's the right one. It's normal gradient. So our 12,600 here. You can simply read the value from this place. So it's 12,600. You can it's 5,355. It's okay. It's acceptable range. Here the reservoir pressure is 5,586. So we are in same range for our data, our reservoir, and we confirmed the overburden. We confirmed the Young's modulus boson ratio. So we need to confirm and we confirmed the reservoir pressure and the overburden and Young's modulus and boson ratio. So we should get accurate stress total or minimum horizontal stress. For drilling purposes, you can check the stress maximum, the maximum stress, the maximum horizontal stress. So simply, by definition, the main parameter that we deal with during fractures propagation is the minimum horizontal stress. We don't really care about the maximum horizontal stress. We care about the maximum horizontal stress if the difference between the minimum horizontal stress and the maximum horizontal stress is low, and there is a value of the value what is the minimum horizontal stress and the maximum horizontal stress is so close to each other, and our fracturing may increase more than the maximum horizontal stress. So it's needed only if there is if the difference between minimum horizontal stress and maximum horizontal stress is very low, and the frac is expected to be to propagate in different direction due to and increase the tortuosity due to this reason. So you can check the minimum horizontal stress and maximum horizontal stress. Then the permeability. For the permeability in GOHFER has some approaches that you need to understand to match. So let's open whiteboard. It's for the permeability. The permeability in GOHFER is assumed to be a K multiplier multiplied by porosity or to the power to the certain other value. So with this value and this value, the K multiplier and the K exponent, so we can get the permeability or estimate the permeability at Basel. So if you press any F1 button on your keyboard, so you can get some recommended values to match the permeability. But here, for example, so our zone is 0.5 millidarcy. So I need to make sure the base zone is 12,600. Our at 12,600 to be 0.5 millidarcy. So we can change the K multiplier. For example, if it's 200, so then we check, and we need to check the value at your base zone. So we need to increase more than that. Let's try 300. We need to match the data from the reservoir activities, from the defect, from the pressure transient analysis or RFT analysis or any source of data from to get the permeability. So using the K multiplier or the K exponent, so we can match the permeability curve with the permeability point that we got from reservoir engineering. So we need to calibrate our for example, here we have good range of data, which if we averaged all this data together, it will give us 0.5 milliliters. Process zone stress is a curve that simulate the fracture propagation at the tip. So it has equation or correlation from the phi E or the effective porosity, and there is some minor curves like the anisotropy and the critical fissure opening pressure. It calculates this critical fissure opening pressure or the pressure at which the fissures will open and the fracture will be activated from the effective porosity. Once you go through to all these curves and you confirm it captured the right one, so and it did the calculated with the right curves, so now you have simply, if you clicked on this, button and change and select MD output curve, output less. So we have a defined geomechanical model for your reservoir. So our reservoir here at 12,600 to 12,700. So this is our bay zones. We have multiple perforation. We'll define the perforation later on, but now we have a good geomechanical parameters where is a lot of data is calculated. So simply we can use this module to calculate the geomechanical parameters and to be for the next steps. Then once you finish any module, you can simply start on this button to go to the next module. We define now the well logging data, the geomechanical parameters using on well logging data, but we need to distribute these properties horizontally and distribute it in a cell in a geological section. So simply once in the previous we select this button, then create new geologic section. And for example, our reservoir is called A6. So it's A6 geologic section. And from this geologic section, there is some general properties for your reservoir, and you need to define the wellbore settings that you will put in your or you implement you uh, in your geologic section. So you need to define some properties, like for example, overburden gradient 1.05 from reservoir porosity, from the data that we get from the uh, reservoir engineer. So it's 6%, 6%. Saturation, it's 25.25%, so it's 0.25. It's oil reservoir, so no gas. Reservoir temperature 300, 230. If you have any other PVT data, you can import it here. Oil viscosity 0.25. Oil viscosity. Reservoir fluid viscosity 0.8. 0.289. So general terms of your reservoir is now and general properties of your reservoir is now defined. Okay. For the water saturation, the gas saturation, oil gas specific gravity 0.89. Oil specific gravity specificity is 41. Then, after you define the general properties of your reservoir, then simply you, you need to define the wellbore strength. So in our case, we have the casing, which is 7-inch. So 7-inch has effective diameter 6.2 inches. So tail depth 12,810. So we need to add a tubing with these parameters, tubing from surface to 8,855 to be I think 7. Oh, okay. So 8,750 okay, so let's open in our well. We have 958 casing till 8,555. Then we have a casing, a liner till TVD. So that the treatment tubing in our case will be 4.5 pH6. Then then 3.5 pH6 tubing. Then we set the bucket at this depth. So based on your based on your tubing that we will use for your design, so you can define the path for your frac flow. So how will we define this in our frac or in our frac design? Simply, we will define the 4.5 pH6 tubing and 3.5 pH6 tubing. So from compression engineer, 4.5 pH6 has ID 3.86 and 3.5 pH6 has ID 2.75 inch. So our treatment both will be 4.5 tubing at till this depth, which is 8,000 uh, 8,700 8,750. So 8,750. Then go to 3.5 tube. If you bump in a casing, 5-inch casing, so simply you will define the 5-inch casing from surface till TD. So we from till depth 8,750, it will be 3.68. Then from ethyl 75 50 till then the frag fluid will go to the casing with depth with the ID 6 wing. Okay, so and we have now the reference well that the same because we checked the box of we will bump at same as the reference well. So we will we define the treatment completion data or treatment string to be on reference well because it's the same as the treatment well. Stage shadowing, it's defined when you have multiple stages or stages that interact with each other. So you can simulate. In this case, you can simulate the stress. You can simulate the fracture propagation in this case. Then we create a geological model with the general parameters that we input and with the log analysis that's done by GOHFER. So this is our grids. So our base zone here. This is the permeability. Has high permeability here. And this is the critical fissure opening pressure. This is the minimum horizontal stress. So we define the grids for our frag propagation. And this is the base zone that's defined by our bit of resist. This is Young's buffer ratio. You need to check all these curves and see the values and get more insights about your reservoir. So I need to check the minimum horizontal stress. If you move to the curve, so you can read the value from this this part. So it's here the minimum horizontal stress is 8,729. So once you know the depths, the values for any depths, for at any depths, you will be familiar with your reservoir. So now we created the grid and created the properties of the reservoir and created the well. This is the well that we created. So what is the next step? The next step is to define the pumping schedule or define a pumping design to check this a pumping design to check the expected treatment data, the pressure and the equipment needed and so on. So let's create a design and call it one. You can, if you have a multiple wells, a lot of wells, simply by this case, you can, by this window, you can select the what is you want to create your design, which will be used. Here's the name of design. You can change as want as you can and put some descriptions as done. For example, you can get done by and so on. So there is different modules to define the pumping schedule in GOHFER. If you prepare for a job, so you can select design schedule. If you are pumping and you need to model your pumping real time, so your laptop is connected with a frag van with the frag pumps. So what is measured by the frag crew or the frag van will be used as for the frag design. So you can select real time. If you review an old job and you need to create a GOHFER model for a previous job, you can select post job. So you can select, we will select the design, and simply you can select perforation. And as per the window, we need, before we select the perforation, we need to check what is the frag fluid, what is the fluid that's in our bore now. So my well is full of now with brine 4% KCl or 7% KCl. Okay, so the well bore fluid is 700 is 7% KCl water. Then in this case we can define our perforation. What is our perforation? Simply we can copy it from our sheet. Once you define a perforation, it's defined here in so in our case it's defined by 6 shot per foot with 20 feet perforation interval. So this is our perforation against this top. Let's add another one. You need to define the number of perf shots for all, not shot per foot, but the number of shots that cover the number of shots that cover your perforation. The last one, 12,600. Number of perforation 144, and this is the diameter from well completion data. And this is the perforation, and this is the perforation against logs. So everything is in perforation is now defined. Okay, so we defined our reservoir, and we defined our perforation, and let's define our pumping schedule. The pumping schedule, simply we define the fluid and the propellant, and how will we pump this pumping schedule. simply create different rows. For example, for our fluid, in from offset data from lab analysis, we decided to bump in this fluid, in this well, and in this formation. We decided to bump a cross-linked gel called high bore H, suitable for our temperature, 230, and simply you can select it as fill down. What about the propellant? In from offset well, from the experience and from the data from this field, we selected the propellant that we will use for this well is 20 high density ceramic 2040 sintered oxide, then fill down. For this job, because we have 20 feet and 20 feet and 24 20 feet and 20 feet and 24 perforation interval, so we need to go to with the maximum bumping rate, and with the current tubing the maximum bumping rate is 36, so I can select the slurry rate to be 32 barrel per minute, and this it's done by once you select one cell, then fill down, it will drop to it will distribute it over the bumping scale. Make sure, because it make a lot of error if we forgot, make sure that the rate in the first cell has a value. When there is no value for the first cell here, the first row, it will give us error, because it needs the rate to start the calculation for bumping scale. So we will use 32 barrel per minute, and for propellant concentration, and for propellant concentration, we will go from 1 ppg to 7 ppg propellant concentration. So we'll start with 1, then 2, then 3, then 4, then 5, then 6, then flush, then shut-in. So, and shut-in, we need to define the rate to be 0. And let's remove the last three rows is not an extra, so let's delete. As the bumping schedule design, so you need to select the bed volume. So what is the bed volume? For our case, I decided to start with 20,000 gallon. You can put a number and see how it will perform in the reservoir. Then go with each stage of propellant to be 7,000 gallon. 7,000 gallon fill down. Then the flush should be the volume of your well, yes, it's 6,900. So for our case, we have shut-in to monitor the shutting during shutting period of your reservoir. So because we didn't define the rate, so we will define by the time. So let's make it two, two, 2 hours. So we defined the pumping schedule to be the bed 20,000 gallon, then each proppant stage 7,000 gallon, then from 1 to 6 ppg, then flush using same fluid, and then shut in for 2 hours. This is the pumping schedule. Now our well is ready for simulation. Let's run the well. So the design. Sometimes there is some errors in the, and this is a good that it happened here. So simply you can save and do repair. Then from engine output, run engine, start the simulation. Now this is the bottom hole pressure. This is the surface pressure. It finished the bed. Start proppant ramping. The rate is 32 barrel per minute. There is our frac job continue to be simulated. So the surface pressure is around 7,000 psi. The pressure is around 10,000 500 psi. We can visualize the propagation. Yeah. You can any parameter that you want to visualize. It's net pressure, viscosity, fracture pressure, fracture width, and we can also visualize it here. The proppant concentration also, if you want to see how it propagates. So the final frac geometry can be seen. We have effective probe half length to be 107 feet, infinite conductivity length 24 feet, average probant concentration 0.925, fracture height is 120, and this is the average conductivity, and there is gross frac length. Gross frac length in GOHFER means the 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 most far away distance of the hydraulic pulse due to pumping. So it is the most far away distance at to which the fluid can reach. So it's not used in the designs. So as a design to evaluate our design, so the fracture half length that will affect in the design, so in the production it will be the estimated flowing length for the frac. Also, in some cases, if I enlarged my pumping schedule, I may need more grids in the output. So I define this number, and most of in our case, in our case, it propagate till the boundaries of our grids. We can simply get rid of that by expanding the the reservoir model that we created. So in grid setup of the geological section, in the grid setup, we can simply change the number of columns, like 2000. Let's make it 2000, but it will make the simulation cost higher. So you may get some delay in the simulation run. Also, if you need to make the size of the grid is smaller, so you can make it one to make the simulation very fine. And the aspect ratio is the ratio between the uh, uh, size of the grid, the aspect, the height, and the length of the grid. So let's see, let's model once we changed the grid. So let's see how it perform. So now we have finer grids, and let's bump again our frag design. Let's see how it will perform. Now take more time. In simulation. Will take a lot of time. You can stop. can make the grids larger again. As you see, so it's took a lot of time to simulate, just 3 minutes. So it's on again. Once you change the grid, it will create again the grid, then it will simulate again. This is so as you see, we increase the number of total grids, and so the frac portion in the grid is some lower. You can visualize the frac width, the viscosity of frac fluid, the net pressure. You can visualize the pressures in the curve in the vector data. Any parameter that you need to visualize, you can visualize it here in grid output port or module. And this scale can be changed simply if you select fracture width. So the minimum value and maximum value here. So you can change the colors. So maximum value 0.5, for example, for the scale. Here we change the scale from this window. So simply you can do whatever you want from grid output window. You can, if you want to use it in a presentation slide, simply you can create records. And if you went to your GOHFER project and your grid setup, your design. So this is a video for the pressure that you created. Sorry. Can put it in the presentation slide. It will take, but you can, as a AVI file, you can import your video in a presentation slide. For GOHFER, if you here is one of the most flexible. You can add any curve for the height, the width, the length. You can copy the engine results in any presentation slide. So it's flexible interface. So you can, any results that you want to extract, you can simply visualize here and make a copy from these charts Also, if you want to get the details and the numbers of the simulation run, so all the details is here. If you open the file vec with the extension vec, so you can find all the data, pumping pressure, surface data, rate, and the propellant, all the data that's simulated. You can find it here, and you can simply copy it and put it in an Excel sheet to visualize and play with the data as you want. And this is simply the design. So we have now the fracture half length, the fracture height, and and the flowing area and the probed area, and so on. So based on the result of this model, you can evaluate your design to be conducted in the field. And that's quick interface for GOHFER. If you want to continue, so simply there is the last module for GOHFER is the production estimate. So once our design, we need to check how it will produce. So simply, if you click production, then you need its simple production module. It's not a fracture, not a reservoir simulator. So it's simple module with one phase flow. So it's just quick evaluation. So you need to define your well, and your frag data is already imported from the fracture simulator. Confirm the reservoir properties, the compressibility, the drainage area, the aspect ratio, oil saturation, water saturation, oil viscosity. All the data that we defined before, and we need to define also the constraints for the production. So we need to know the maximum production. So as we will run the pump, so we need to constrain the production for a year, 360 days, with constant pressure, bottom hole pressure to be 500 psi. Then run production estimation to be how to get how our well will produce. It will start the production with liquid 900 barrel per day. This is the liquid, oil, gas, and water rate. So based on our design, and on this well will produce with this rate. I personally tried this module, and it worked well in oil well, whereas there is one phase flow that's produced from our reservoir. It's a very simple model. So once you get the data from the reservoir, so you can simulate. If you have a data before frag, simply check the unstimulated well, then run production. Then it will show the production with frag and the production without frag. So in our well, unstimulated oil and stimulated oil. So without frag, it will produce 100 barrel per day. With frag, it will produce 900, and this is the drop during the production curve, estimated production curve for our design. This is simply the modules for GOHFER. I just used this module with you today was in our 2-hour session. I hope you get some experience with GOHFER. This is the main workflow. You create a reservoir grid. You work with the logging data to get geomechanical parameters. From the geomechanical parameters, you create grids. Then you create this grid is called geological section. Then create a design. Then work with the design from the first step is to check the wellbore fluid, then define the perforation, define the pumping schedule, run this pumping schedule, and then estimate the production. This is simply the main workflow for GOHFER. Is there any question for in GOHFER till now? Is there any question? If you have any question, you can type it in the section, in the QA section, or mute your mic.
I have a question.
Okay, thank you for attending today, and I hope you have a question. Okay, sorry,
I'm just wondering, like, how long does it take to get comfortable with all this?
I think if you spend 3 hours on GOHFER, it will make you with good experience. So make around 2 or 3 hours on GOHFER, then you will get familiarized with all the modules. The interface is very easy in the design parts. For sure, there is a diagnostic part that can use to interpret the mini-frag and defect data, more details in, but the main workflow is explained today. So I think to get familiarized, I think not more than 3 hours to get a good experience with GOHFER.
Thank you.
Yeah, is there any question? Thank you for attending today, and thank you.
Thank you.
Thank you.